Well, class. All right, so we're going to talk about 2D collisions today. So basically the same principle applies. Conservation of momentum. So just like before, we have P equals P prime, except now we are dealing with vectors. And the only way two vectors can be equal to each other is if their components are equal to each other. So basically what we have is Px equals Px prime and Py equals Py prime. And so momentum in the x direction is conserved, and momentum in the y direction is conserved. Actually, I'm going to write a third. Momentum in the z direction is conserved as well. And so let's say we have, just in general, like if the momentum in, let's say we have two objects moving in the plane, like say this board is a plane, then Pz would be equal to 0 before the collision, and it's going to be equal to 0 after the collision as well. So, this is conservation of momentum in general for, well, I guess 3D collisions, just collisions in three-dimensional space. Each component of momentum is conserved. And again, this, in each case, this is the momentum of the entire system. So let's look at maybe a general example, maybe not solve it, but just kind of set it up. Let's look at the most general two-dimensional collision. Let's say we have M1, and let's say, we'll say that's moving along the x-axis with a velocity v1, and mass 2 is moving with a velocity v2. Actually, let's, maybe we won't solve this, but let's just make up numbers. Let's say this is 10 meters per second. And for mass 2, let's give this angle, say it's moving 8 meters per second. At an angle, like I drew it with respect to the y-axis. Let's say in this problem, theta is 30 degrees. And, I'm going to move the setup over here. I think I have more space on the right board. And this angle is 30 degrees. So I'm going to erase this board on the right. We'll set up our equations here. So again, and we know the masses. I'll just write down some numbers for that. 6 kilograms, and say M2 is 4 kilograms. So let's at least set up this problem. So let's find the momentum. Let's look at mass 1. Let's make a table. Actually, let's put this here. Say we have P1, P2, and P. So this is, P1 is just the momentum of mass 1, P2 is the momentum of mass 2, and then we can add those up to get the momentum of the system beforehand. And again, these are in, say, kilogram meters per second. So we can just put the numbers here. And this is just before the collision. Now again, we know everything that happens before the collision. And again, it's the exact same principle that applies. Momentum is conserved. We're going to see that this is much more difficult than the case of a one-dimensional collision. Because remember, in one dimension, our goal is to find the velocities after the collision. There's two objects, so there's two unknowns. But here, we want to find the velocities after the collision. What we want are v1 prime and v2 prime, where both of these are vectors. And so we have four unknowns. We have v1 x prime, v1 y prime, v2 x prime, and v2 y prime. And so we're going to need to know a lot more information to solve these two-dimensional collisions. And that is actually something that we should expect to be the case. But let's set up what we do know. Remember, we know everything about the beginning. So, we could fill that out. So for mass 1, it's 6 kilograms moving at 10 meters per second. And this one is purely in the x direction. So all the momentum is in the x direction. Now P2 in magnitude is 8 times 4 is 32 meters per second, or kilogram meters per second. And we have an angle of 30 degrees, so sine of 30 is 1/2. So that would be 16 in the x direction, or minus 16 in the x direction. Cosine of 30 is around 0.87. So let's say 27.8 in the y direction. And we can add these up. So we have the total momentum of the system in our xy plane. It's 44 in the x direction, 27.8 in the y direction, in units of kilogram meters per second. But again, we have no idea what's going to happen after the collision. We have four unknowns. So after the collision, in general, if we just write after the collision, we don't know what direction each individual particle is moving. So let's just write P prime, let's write P1 prime. Again, velocity, mass 1 can be moving in a somewhat arbitrary direction. And I say somewhat. The only thing we know for sure is the y component of velocity is not going to be negative. Because this velocity is hitting it, it's initially moving just purely in the x direction. It has no motion in the y direction. So if it gets hit by an object moving in the positive y direction, it's going to knock it in that direction. But that's really all we know. So what we know is we have m1 v1 x prime plus m2 v2 x prime, we just want the momentum of object 1 first. That would be m1 v1y prime. So whenever we need to know both of those components to find p1x. And similarly for the momentum, p2, the x component would be m2, these are primed, we're looking at after the collision. So the x component of the momentum of mass 2 after the collision is mass 2 times the x component of its velocity. And similarly with the y direction. And so if we add these up, we can write down an equation. Let's look in the x direction. and in the y direction. So in the x direction, the total momentum of the system would just be, p1x prime plus p2x prime. So we have m1. Let's put the number in here. So what I'm going to do is we're going to have kilograms on both sides. So I'm going to write m1 just as the number 6, v1x prime plus 4 v2x prime. So we divided by a kilogram. So total momentum in the x direction would be 44. That would be kilogram meters per second, but we divided by a kilogram. So we'd have that equation. And then in the y direction, we'd have 6 v1y prime plus 4 v2y prime equals 27.8. Oh, I said y direction here. Well, let's just write down the result. So this is what we get by saying P equals P prime. And so we have two equations with 4 unknowns. And we basically need at least 2 more pieces of information to be able to solve this equation, or this system of equations. So one thing I could do, if I was giving you a problem like this, I could give you the velocity of one of the particles after the collision, but I'd have to give you both of the components. So that'd be like the 2 additional pieces of information, and then you could solve this system to get the remaining 2. So basically, the idea is that principles are the same, but mathematically things can get significantly more complicated. We're dealing with systems of equations now. And so usually I'm kind of limited in what I can ask on this topic. Now you might think, what about an elastic collision? Is that still a completely solvable problem? And the answer is no. The mathematical reason is that kinetic energy is a scalar, so it doesn't give us as much information as a vector equation would. So like conservation of momentum, P equals P prime, that's a vector equation. That's actually 2 scalar equations. Or if we write down conservation of kinetic energy, that gives us 1 equation. So we'd have 3 equations with 4 unknowns. So that can simplify the problem in the sense that it gives us another equation to work with. But still, even in the case of an elastic collision, in general, that is not solvable. And I give you a mathematical reason for that. But maybe a more obvious reason, we should have expected that result. Let's say we have 2 particles collide elastically. Let's say this is a top view, so we're looking at 2 objects that are going to collide. Let's say a head-on collision. Now you might think this is a one-dimensional problem because they're moving in the same direction, but what if they don't hit each other perfectly? Like say these are 2 hockey pucks. And if they hit perfectly, they'll just bounce off each other. But if they're offset, if their velocities don't hit, they're offset a little bit, then when they collide, they're going to go off in different directions. So there's a problem in the book that deals with something like this. And again, you would expect that a very important factor in how these things are going to respond to the collision is how offset they are when they hit each other. So if they're almost like dead center, they're going to mostly bounce off each other. Or if there's a significant difference between them, they could go off at greater angles. And so, even if it's an elastic collision, just the way that they hit each other is definitely a factor. So 2-dimensional collisions, a lot to work with, a lot to, just mathematically much more complicated. So I kind of limit things in what what kind of questions I can actually ask. However, there's one case that can be reasonably dealt with, and that is a perfectly inelastic collision. If the objects stick together, that's a more manageable problem. And we'll do an example of that in class during the discussion. So we kind of just set up the idea of a two-dimensional collision, but then we will work out a detailed example in class, actually next Monday, because we have lab tomorrow. But I want to talk about another topic. I'm going to pause this video for a second. All right. So we set up the idea of a two-dimensional collision. I want to revisit the idea of center of mass. So we define center of mass in one dimension. Let's say we have two objects in a line. M1 and M2. And we can pick our origin anywhere we want. So I won't even write it down. But generally, we can say that XCM would be M1 X1 plus M2 X2. And I'm going to divide by capital M, where M is the mass of our system. So if we have two particles, M is just M1, M2. Now, again, this is easy to generalize to any number of particles. So if we had a third particle, we'd have M1, X1 plus M2, X2 plus M3, X3, divided by M, which would just be the total mass of our system. So I just write down the equation this way. But again, if these masses are moving, like right now, let's say M1 is bigger, so the center of mass would be closer to mass 1 than mass 2. Now, if the masses are moving, the center of mass is also going to be moving. So we can talk about the velocity of the center of mass. That would be M1 V1 plus M2 V2 over M. Okay, now, we showed this in class. We'll look at sometime delta t later, and we kind of write down another equation, do a subtraction. We showed this result. Now, it's interesting. Let's look at this numerator, M1 V1 plus M2 V2. That is the momentum of the system. And M is the total mass of the system. So we can write it like this. Or if we multiply by big M, we can say that the momentum of the system, I don't know why I put that prime there. So the momentum of a system is the mass times the velocity of the center of mass of the system. And it's pretty amazing. Like, we started out with Newton's second law for a particle, where we said the net force is equal to the change of momentum of the particle over time. And then we were able to show that the net force acting on a system of particles was equal to the change in momentum of the system over time. You can write both of these as vectors. So this is for a single particle, but the same kind of equation applies if we generalize to a system of particles. And similarly, the momentum of a single particle is its mass times its velocity. For a system of particles, the momentum of the system is equal to the total mass of the system times the velocity of the center of mass of the system. And this is actually a useful fact, but not something that we're going to do in this class. But conservational momentum is a kind of like a fundamental principle of physics. It's just true. And coordinate systems are things that we make up. So they're we would expect a fundamental principle of physics to apply in any coordinate system. Well, any inertial coordinate system. And so we could consider momentum, like we could look at momentum in different reference frames, and we would expect that conservation of momentum would still apply, and it does. And there are some cases where looking at collisions, because you can see that some of these problems get fairly complicated, sometimes if we actually switch to this center of mass reference frame, it makes things easier to analyze. So if we have a collision problem, we can just deal with it directly in like what we call like a lab frame, where we're considering ourselves at rest and both these objects are moving. But if we just switch reference frames, we know how to do that by using our rules for, like with a subscript and all that. Sometimes switching to a frame, so if you look at a collision, if you picture yourself moving along with the center of mass of the system, sometimes a collision is much easier to deal with. And there is, I think there's a suggested problem where I talk about that. And either that or it's something in the worksheet. Forgot which one. Yeah, I think it was in that worksheet. Yeah, so, where this idea of momentum being carried over to the, applying it to the system, where this equation applies to systems as well, as long as we consider the velocity of the center of mass, that is very useful, that can be very useful. Only one problem we're going to deal with though, it's in that worksheet. But I also wanted to generalize this idea of center of mass. What if we have mass 3 and we put it over here? Now where is the center of, like this concept of center of mass? Now we're dealing with an XY plane. So the center of mass is going to be somewhere inside this region. And I'll just pick somewhere, let's say it's right here. This is the center of mass. How do we find that point? And I'm going to erase this. And to start with, this equation, perfectly valid. This does not change. So the center of mass has components. It has an x component and a y component. And the x, now we have x3. Because we have 3 masses. So to find the x component of the center of mass, we only look at the x components of where the masses are located. So in this case, M3 is up here. If we moved M3 down to the origin, or down to the x-axis, that would not change the x-coordinate of the center of mass at all. It would pull the center of mass down. If all 3 objects are on this line, then the center of mass would also have to be on that line. But yeah, moving a mass in the x direction has no effect on the location, the x component of the center of mass. And similarly, the y component of the center of mass only depends on the y components, or the y coordinates. And again, in this case, m would be m1 plus m2. In general, you just add up all the masses. So we'd have m3 here. Okay, so, and again, same thing with the velocity. we'd look at like the x component of the velocity of center of mass. We'd look at the x component of each of the velocities of the individual particles. But same formula as before. But again, you just only in the x direction, you only look at the x components of the individual pieces of it, and similarly in the y direction. And so I think that'll be it for this topic. Two-dimensional equations, much more difficult to deal with. So we'll go over an example of the kind I would expect that would be reasonable for this class, where we just look at like a perfectly inelastic equation where things stick together. But that'll be it for now.